my name is Kate Lyons. I'm a scientist with the Evolution of Terrestrial Ecosystems program in paleobiology. And today I'm going to be talking to you about work I've been doing with colleagues in New Mexico about whether the extinction of the large mammals could have had an effect on climate. Now, this work came about because my colleague Felisa was listening to NPR Wait, Wait, Don't Tell Me, and they were making fun of a study that calculated that one full-grown moose expels annually the methane equivalent of about 2,100 kilograms of carbon dioxide emissions, which is equivalent to about 13,000 kilometers of car travel, or 2 long-haul flights between Oslo and Santiago. So we got to thinking, if one moose expels that much methane, what about the megafauna? Could the megafauna have had a detectable effect on global biogeochemistry? And there's some reason to think that they might have. Of the species that went extinct in the Americas, in North America, 53 of them were herbivores. In South America, 61 of them were herbivores. And it's the herbivores that are the ones that are producing the methane. We know that this extinction was highly size biased. So this is showing the body size distribution of mammals on 4 different continents. The species that survived the extinction are in white. The ones that went extinct are in red. And you can see that the red is all over on the right-hand side of the graph. So pretty much if you were a large mammal, you were much, much more likely to go extinct. There have been a number of comprehensive reviews that have looked at this particular extinction, and the consensus is coming out that humans probably had something to do with this, and this will become important at the very end. Then we also know that the bigger a mammal is, the more methane that it expels. So this is data derived from modern mammals showing the relationship between methane emissions per year in kilograms and body mass. And you can see that there is a linear relationship for both foregut and hindgut fermenters, and that bigger mammals expel more methane per year. So in order to determine how much methane the megafauna could have been producing, we calculated this as the product of a species-specific methane emission per year. We used the allometric relationship between body size and methane that I just showed you to calculate methane emissions for each species. We evaluated density based on the relationship between density and body mass, and then we estimated geographic ranges of Pleistocene species, and the product of that gives you the methane production per year of a single species. We sum that up over all 114 extinct herbivores to get the amount that the extinct megafauna would have been producing on a yearly basis. And we come up with a median estimate of 9.6 teragrams per year was lost with the extinction of the megafauna. And this is the lower end of the estimate. Our upper end was about 25 teragrams per year, and that has to do with how you estimate geographic range. So the next question is, did this drop in methane or this loss of megafauna correspond with a loss in methane concentrations globally at this time? So it turns out that it did. This is the methane concentration taken from an ice core from Greenland, and you can see that there was indeed a drop in methane around the time of the extinction of the megafauna. So in the pinkish part, you can see I've outlined the oldest Clovis artifacts. That's the entrance of humans into North America about 13.4 thousand years ago. Very rapidly after that, there was a drop in methane, and it's coincident with the Younger Dryas cold snap. This is a period where climate was anywhere between 9 and 12 degrees Celsius colder than it is today. So you can see that humans arrived on the continent, megafauna populations started decreasing and going extinct, and there was a coincident drop in methane. So the next question, though, is whether or not there was anything different about this drop in methane. Methane waxes and wanes over time. In glacial periods, it's about 300 to 400 parts per billion. In interglacials, it's about 600 to 700 parts per billion. So we needed to ask whether or not this was different from previous drops. So to do that, we used an ice core from Antarctica this time that had a longer time period to it, and we compared the 4 biggest drops over the last 500,000 years to the Younger Dryas drop, and asked whether or not there was anything different. Was it bigger in magnitude? Was it faster? And it turns out it's not bigger in magnitude, but it is much faster. The methane drop at the Younger Dryas is 2 to 4 times more abrupt than any of these previous drops. And you can also differentiate the source of the methane, whether it's animal-derived or not, and the isotopic signature of the methane was different. During the last deglaciation, the largest source of methane was megafauna, and that's not true for the deglaciation or during the Holocene. Okay, so if megafauna produced 9.6 teragrams per year, what effect could that have had on atmospheric concentrations? So ice cores suggest a drop of between 185 to 245 parts per billion. Residence time of methane in the atmosphere varies a little bit with temperature, so we had to bracket this, but this translates to a decrease in the global source pool of about 7 to 77 teragrams per year. This is equivalent to 50 million to 500 million of those NPR car trips. So what that suggests then is that this drop in methane, the loss of the megafauna, could have explained between 12.5% and 100% of the drop in methane at the Younger Dryas. So what does this mean? The arrival of humans into the Americas and the subsequent extinction of the megafauna coincided with a decrease in atmospheric methane that was significantly more abrupt than previous intervals. Our computations suggest that this was a drop of around 9.6 teragrams, and the megafaunal extinction probably explains anywhere from 12.5% to 100% of this decrease. If the late Pleistocene extinction of the megafauna contributed to the Younger Dryas cold snap, then this suggests that humans indirectly contributed to the onset of the Younger Dryas cold episode, that human influence on biogeochemical cycles are detectable well before the Holocene, and that the Anthropocene should be recalibrated to 3.4 thousand years ago. Thank you. No? Sorry, I don't have time for a question.
Speaking of human influence, has anyone thought of applying this on a different scale to obesity in humans?
You know, that's a really good question, and nobody has done it that way, but there are some people, Jim Brown out of New Mexico has been looking at human population energy acquisition use relative to other mammals, and has shown that humans are equivalent to a 60,000 kilogram primate in terms of energy use.